All right, I'm going to go through these fairly quickly, but do remember you can always come to me for a much slower explanation if you'd like. I can give you similar examples, things like that. The first one here, what's wrong with this expression? And let me get my, not that, oh, down here. Here we go. All right. Um, so what's wrong with the following mathematical expression? Well, this right here, 4 divides into 12 is a statement that's either true or false, and this turns out to be true. It's called a Boolean in computer science. In our class, we called it a proposition. So this is a true or false statement. This is an integer, which is a totally different. They're two different things. So the reason it's not saying you couldn't fix this by doing 12 goes into 4. That's a false statement, but it's still a Boolean. It's not an integer. They're two completely separate things. Most importantly, this is not the same type of thing as this. This, it would be okay to say 12 divided by 4 equals 3, because this is an operation that you're performing that ends in an integer, and this is an integer. So both sides here are equal to an integer. So different types of expressions. Here we're looking for every integer, the set of all integers, such that 4 goes into the integer and the integer goes into 12, or the 4 divides into the integer divides into 12. So if we think of integers that 4 divides into, well, we could start with 0, 4, 8, 12, 16, and so on. But we'd also, because it's integers includes positive and negative, we would also include ones like negative 4, negative 8, negative 12, negative 16, and so on. So, and if that seems weird to say that 4 divides into negative 8, let's look at that real quickly. So the definition of divides into means we can think of an integer times the first one. So 4 times some integer equals negative 8. Is that true? It is. 4 times negative 2 equals negative 8. So this is a valid statement. It's a true proposition. And then x divides into 12. Notice 0 does not divide into 12. There's no integer we can multiply by 0 to get 12. But 1, 2, 3, 4, 6, and 12 all divide into 12, as well as the positive and negative versions of all of those. So I'm just going to put positive and negative here temporarily. Now let's work with that second set. We notice we have to have and, so we have to be in both sets here. Let me switch some colors here. So 1, 2, and 3 are not in that first set, so they're not going to count. And 6 also is not, 4 does not divide into 6. 4 does divide into 4 and 12, and negative 4 and negative 12. So the final answer here is negative 4, positive 4, negative 12, positive 12. That's all the elements in the set A. Using the definition of even or odd, explain whether 0 is even, odd, or neither. Well, the definition of even is an is 2k where k is an integer. So if we can come up with a k that we multiply by 2 to get 0, if we can come up with an integer that we multiply 2 to get 0, then it's even. And indeed, 2 times 0 equals 0. And because 0 is an integer, we can say that 0 is even. Any integer multiplied by 2 is going to be an even number. And if you have a number and you can multiply 2 times some integer to get that number, then that number is even. All right, determine whether it's true or false. So this first one here, get rid of that guy. I'm not sure what all that is. 1 plus 1 equals 3, if and only if 7 greater than 8. So this one was in the Jeopardy review, and basically this is false, and this is false, and if and only if we want to put that in terms of logic symbols, is this double implication or biconditional. And the way this is true is if the values on each side are the same. So if they're both true or they're both false, then the overall biconditional is true, and that's what we have here. So it's true. And then you don't have to put this, but basically it's called vacuously true, because as long as you have an implication and the if part is false, then the entire implication is true. And since the implication going both ways is false, the if part of it, then it's called vacuously true. All right, let's try. If x plus y is even, then x and y must both be even. You could try a few to play around. This is false. Consider x equals 1, y equals 1. Now you could have them different, could have them the same. When it's written like this, x and y are allowed to be the same or different, but it doesn't really matter here. X plus y is 2, which is even, but x and y are both odd. So this is a single counterexample. Now remember, if you had a single example of, say, x equals 2, y equals 6, then yeah, x plus y is even, but the way this is phrased, it's a universal claim, which means if you just come up with one case where it's not true, then the entire thing's not true. All right, so here we have a couple sets. Let's start off listing the elements. So A is all the natural numbers that are at least as great as 5, but less than 10. So it's going to look like that. We want to be strictly less than 10, but we do include the 5 because of that equal sign. And then B, also natural numbers. We only want the multiples of 3 that are less than 12. So 0 here. Remember the natural, when it's written like this, starts at 1. The non-negative naturals would be like this symbol right here, and that's on the definition and theorems sheet. But here we have natural numbers that are multiple of 3 less than 12, so we only have 3, 6, and 9, not too many of those. Draw a Venn diagram. Okay, so here we have A and B. And you could actually put the specific elements in here. We're just going to write the total numbers. So 6 and 9, there's 2 elements that are in both sets. There's 3 elements in A that aren't in B. And there's only one here, the 3, that's in B and not in A. And then here, the region outside of A and B is not defined, so I'm going to change that in the instructions here. We need some universal set, which I never defined here, so we're just going to cross that out. If there was a universal set, then anything in the universal set not in these two would be part of the outside region. So here we only have six elements. So A union B, that's anything that's in either one of them. So basically the 3 and then everything in A. A intersect B is talking about the 2 that are in A and are in B, which are only the 6 and the 9. This is the Cartesian product. So this is where we'd be taking things like 5, 3, 5, 6. You're taking the first element from A, the second element from B, and you're coming up with as many as you can. So we do all the 5s, and then we go to the 6, 3, 6, 6. You might start to see this rectangle form. Basically, since there's 3 in B, we're always going to have 3 in that second one. There's 5 in A, so we're going to have 5 different lead numbers. So 5 times 3 gives you 15. Remember, the bars say what's the size, what's the cardinality there. A take away B, so everything in A except the things in B. So the 5 would be there, 6 would not be there because it gets taken away by B. The 7, 8, the 9 would not be there because it gets taken away by B. And power set of B, so this is all the subsets, the set of all the subsets of B. So that would include 3, 6, 9, the empty set should include that. Everything with 2 elements, so that would give us 3, 6, 3, 9, 6, 9, and then the only one we have missing yet is if we get all 3 of them in there at once, 3, 6, 9. So we can count 1, 2, 3, 4, 5, 6, 7, 8. So the number of elements is 8. We'll see this several times in the discrete math course. A shortcut that we can do here would be 2 to whatever the cardinality of B is. 2 to the power of however many elements are in B. In this case, there's 3 elements in B, so 2 to the third would give us 8. We'll see later how we come up with this formula and prove it. Okay, true or false, explain or provide a counterexample. There exists a natural number such that for any natural number you choose, or sorry, such that there exists a natural number such that for any natural number you come up with, the A divides into B. In other words, there's a natural number that every natural number divides into. And that's false. The one that could potentially be true would be if B is 0, because we do know every integer divides into 0. Multiply by 0, you get 0. But 0 is not in the natural numbers, so that's not eligible. And there's no other number. Now, we would have, if it said there exists an A such that for any B, A divides into it, then that would be true because A could be 1. 1 divides into every natural number, but that's not what we're saying. We're saying there exists a B that every A divides into. And once we choose the B, it freezes, and that same B has to work for every A because of the order that this is in. So this is false. And why is that? I guess one thing you could say, whenever you're with natural numbers and you have a divides into, A has to be less than or equal to B, and so you could always choose an A that's bigger than B that would make it not work, I guess is one way you could explain that. For every natural number, there exists an integer such that A is less than that. Yeah, true. Consider B plus 1. Sorry, A plus 1 equals B. So think about this. No matter what, you get to choose the natural number first. Whatever you choose, I'll just choose the integer that's one above that, and that'll guarantee that my B is greater than that. So notice in this case, the person gets to choose their integer after A is already chosen. So they can guarantee whatever the person chose, they can just add 1 onto it and make sure they're higher. Okay, sum of 3 consecutive integers is always a multiple of 4. False. Consider, I don't know, 1, 2, 3. So the sum is 6, which is not a multiple of 4.